equations from both the left side and the right side of the beam. So if you usually take your equation from the left side of the beam or the right side of the beam, this is good practice to make sure you can do it both ways. Sorry, I'm a little sick right now. So first things first, we're going to want to solve for our reactions. And I guess we could solve them here. You really should know how to do this already, but we can run through it real quick. So first, we want to note our positive convention. So we know that counterclockwise rotations are positive, and anything in this quadrant is positive. So let's start with some of the forces in the y equaling 0. I'm just going to use statics to really get through this. 0 equals, we have reactions here. We're going to call this AY and DY. Those are the only reactions in the y direction, and they're pointed upwards. So we have AY plus DY minus this 18K going down. 18, this is kips, but I'm going to keep writing it as K, minus the force, the distributed load here, which is going to be 2.4 kips per foot times the total distance that it is, which would be 16 feet times 16 feet, and then canceling our units will give us the total load positioned at the center of the midpoint of the distributed load. So we can write an equation for AY. AY equals, I'm going to swing everything to the other side. It's going to be 18K plus, this is going to be 38.4K minus dy. Now that we don't know dy, so we're going to need a second equation. We have one equation right now, two unknowns, so we need another equation. So I'm going to sum the moments about A and set that equal to 0. So we'll have 0 equals dy time, so about the point A right here, the total distance to dy would be 24 feet. And then we have the 18 rotating downward like that, about point A. So that would be minus 18 times 6, the distance from A to 6, or 8, yeah, from A to B, the point load. Minus, again, remember as I said, the 38.4 force is going to be positioned at the center of the distributed load, which would be 38.4 times, I don't know why I'm changing my convention here, times 8 feet. And I kind of dropped using units here. But solving for dy, we get that dy equals 17.3K. So I'll underline that. And then plugging it back into here, we'll get that AY, a little sloppy, AY equals 39.1 kips. So now that we have our reactions, we can start writing equations. So to begin, I'm going to start with starting on the right side of the beam. So let's write the moment equation for what goes on at the right side of the beam. So you can pause it and do whatever you want now, and let's get started. So when I'm going to draw a line here and say this distance, not a good line, this one is distance x. This is distance x. So let's say x is between 0, greater than or equal to 0, but less than 6. So it's basically what I'm saying is x is at or right infinitesimally close to that point. Okay, so that would be 0 feet and 6 feet. So let's draw the beam. And what's happening at this point here? Well, we know at point 0 we have a reaction here. We have our AY. And we also have this distributed load going along here of 2.4 kips per foot. I'm not going to write the unit, but I am going to try and clean that up. It's going to be 2.4. I'm going to blow my nose now. Here we go. Sorry. I am still not really feeling well, so sorry about this. Oh, man. Wow. Okay, sorry about that. So between 0, so this point being, this point being 0, and this point being infinitely close to 6, we know that this distance here is x. Okay, so let's go ahead and erase that. And well, when we made our cut right right before infinitely close to 6, as I keep saying. So we have a shear force going down, and we have a reactive moment as well. I just usually point the moment in the positive direction. So like if this is the whole beam, if I'm going to make my cut here, I'm basically saying that it's going to be like that. Like the beam is frowning. Okay? So that's normally what I do when I make my cut to a beam. Is I'll normally, if I'm cutting from this way, I'll position the arrow like that. And if I'm cutting from this way, I'll position the arrow like that. Okay, cool. Okay, so let's start writing our equations. Okay, so let's go ahead and squiggle these out of here to not confuse anyone. Okay, so some of the forces in the y. Now we're just doing statics, right? So 0 equals ay minus v minus 2.4 kips per foot times x feet, because we don't know how long that is going to be. So we're going to solve for our shear equation. V equals ay minus 2.4x, and of course we know what ay is. It's going to be 39.1 kips. Yep, right there. So that's the equation for the shear. You have two different ways to do this. You can either integrate this, because the moment is the integral of the shear. It would take too long for me to explain right now, but all you really need to know is like the moment is the integral of the shear diagram. And once you start to realize how that works, it makes problem solving so much easier. But you run it, if you integrate this, you get like if you integrate it, you'll get like 39.1 0.1 x minus 1.2 x squared plus c. And it's like, well, what's plus c? So the easier way to do it would just be to solve for the moment equation. So let's do that. Okay, so we'll do sum of the moments about my point equals 0, and my point being right here. Okay, so let's do this, and let's go ahead and do this. So 0 equals, again, when you're summing moments and you have a moment, you're not multiplying by a moment arm or anything, you're just adding it. So it's going to be, if we have our positive convention like this will be m plus, okay, here's going to get tricky now, 2.4x times x over 2. Now this is because when you do a distributed load, you multiply this area, this number times the base, and then you divide that by 2, and that's where the point load is. That's where the point load is on the beam. So however long x is, the resultant force for the distributed load will be half of whatever x is. Okay, hopefully I explained that well. So that's that point, and then plus, or this is minus the reaction. So minus, because it's rotating us counterclockwise, so it's rotating us this way. So it would be minus AYX. Okay, So let's solve for our moment here. Again, we know what AY is. I just like writing it in variable. M would equal minus 1.2 x squared plus 39.1 x. Now, of course, plus c in this situation would equal 0. And I think that's because you're starting at for the beam where you're starting at a point in the beam that equals 0. I think, I don't know, I just kind of solved it and didn't really go into the theory behind it all. So this is the moment equation uh, from x equals 0 to x equals 6. Okay, so I'll underline that in purple. So that's one part. Okay, right. Okay, so from x equals 0 to x equals 16. So let's do now, we're going to do the another cut at a much larger portion of the beam. Okay, so now we're going to cut. Before we made our cut, here. Now we're going to make our cut here. Okay, hopefully you guys got that. So now we're going to have x between is greater than or equal to 0, and x is infinitely close to 16 feet. Okay, so let's go ahead and draw the beam again. Okay, not really my best beam, but that's all right. We have the distributed load. Now, the distributed load is going across. This is the entire distributed load. Okay, and we also have our 18 force, our 18 kip force here. So this is 18, and then this is 2.4. And then the dimensions are very important here to make sure you get correct. But let's keep drawing what we have, the forces we have. We have a y, and we have the shear and the and the moment. Shear pointing down, moment going counterclockwise. Now, like I said, the dimensions are important here. So from the beam in the initial problem, we know that the 18K force is 6 feet away. So we know that this is 6, and we're going to say that this distance here is x. Okay? So that means that if this distance is x, then this whole thing from here to here is going to equal x plus 6. It's simply this plus that is, well, this plus that. It's, it doesn't really get simpler than that. So let's go ahead and solve for the shear equation and get the moment equation from that. It's going to be a lot of terms, but just keep track of your terms and you should be good. So sum of the forces in the y equals 0. 0 equals AY minus V minus 18 minus 2.4 times the total distance, x plus 6. Okay? I mean, I feel like that was pretty easy. I don't really feel like I have to explain anything there. So solving for V, now we get minus 2.4x plus 6.7, because now we can plug in for AY, and you just move your variables around, and you can solve for V. So like I said, you can integrate this, but then you're not going to know what your plus C is. So you kind of have to solve for the point you have to solve for the moment equation to get that plus what's your constant is. So let's go ahead and do that. So again, my point being here, we're going to sum the moments around my point, set it equal to 0. So 0 equals, here we go, the moment again, minus AY, because it's rotating us this way, AY, the total length of the beam, x plus 6, plus 18, rotating us this way, x plus 2.4, the distributed load, times the total distance, because it's the total thing, times the total distance, okay, times x plus 6. And then what did I say about the distributed load? Its resulting force will be at the center. Excuse me, I'm talking too much. So it would be at the total distance, x plus 6 divided by 2. I'm going to rewrite this with my parentheses, how I have it here. X plus 6 over 2. Okay, so it's a little annoying to solve. I'm going to break it down in one more step, and then I'm just going to write what the solution is. So how I did this was what I solved for m. So m equals ay x plus 6 minus 18x minus 2.4. Oh, so sorry. That was really gross. I apologize. Actually, I'm really writing it the same as I have up here, so I'm going to write it in the next step. I broke this down. I did some foiling here, and I got m equals to 39 point. Ooh, that's a horrible 9. 39.1 x plus 234.6 minus 18 x minus 2.4. Here we go. X squared over 2 plus 3x plus 18. And then you just go ahead and just mess with that, and you can solve for m. It equals 6.7x minus 1.2x squared plus 191.4. So here's the most important part of this problem. So let's go ahead and say, so this whole time we've been working up to this moment right here, because we want to know, this is the equation for the moment from 0 to 16, which is right here, right? And the whole point of the problem is verify both ways give the same value for the moment at C. So we can use this equation to solve for the moment at C. So at x equals, where does x have to be? Where does this x, have to be so that this is point C? Let's go ahead and scroll up here. It has to equal 10. So at x equals 10, the moment at x equals 10 equals 138.4 kips feet. Okay? So now, simple enough. This is actually the harder side. Now we just have to go, this is from the left side of the beam. Now we have to go from the right side of the beam. Okay? So now we're going to go we're going to make a different cut. We've been making cuts. We made a cut here. We made a cut here. From this way. Now oh boy. Now we're going to make a cut here from this way. Okay, so let's go ahead and do that. So if x is in between 16, oh wait, it would be x is infinitely close to 16. Well, x is in between 16 and 24. Okay, let's just do that now. It's infinitely close to 16 and can be at the end of 24 feet. Okay, so let's go ahead and draw that. I mean, and it's going to be simple enough. Between this is point 16 and this is point 24, I mean, there's nothing here. So simply enough, it's going to look, ta-da, this point is x, we have this point as dy, dy. This is our shear, and as I say before, that's how I'm going to draw my moment. Using statics, sum of the forces in the y equals 0. 0 equals dy minus v. So the equation for the shear going from the right side of the beam is equal to 17.3, which is the reaction at dy. It's one of the first things we solved for. And like, you can also integrate this, and you can also solve for the moment, just as we did using statics about this point here. But it's kind of obvious to see that the equation for the moment is equal to 17.3x. So if we were to plug in what value does x have to be for this to be point C, it would be 8. So at 8 equals 138.4 kips feet. Congratulations, you just solved your problem. I'm going to stop recording now before I throw up.